Okay, so again, we're going to look at the analysis for the common mode gain of our circuit. So here we have on the left our differential amplifier, but this time we're feeding it with a common mode input voltage, VIC, that's tied to both gates of M1 and M2. Now again, we note that we have perfect symmetry, M1 is equal to M2, and the drain resistors, RD, are equal to one another. So RD1 is equal to RD2 is equal to RD. Now, we can split our current source up into two equivalent current sources where half of the current source is flowing through M1 and half of the current source is flowing through M2 because of the symmetry. Likewise, we can split the resistor into two equivalent resistors where RS is equal to 2RS. This way, when we recombine the resistors, it would equal a single RS. In other words, 2RS in parallel with 2RS is equal to 1RS. Now we note that again we have symmetry, so we can draw a half circuit. Here is our half circuit. We have a drain resistance RD, we have a transistor, and then we have a source resistance 2RS. Now again we know that our voltage gain AV is equal to minus GM R total. We'll again keep assuming that the output resistance of the transistor is quite large. Here we can say that GM is equal to minus little gm divided by 1 plus little gm times the total resistance we see in the source, which is 2RS. We know that R total is approximately equal to RD, so we can say that our common mode voltage gain, VOC divided by VIC, is approximately equal to minus GM RD divided by 1 plus GM times 2RS. Now, we know our differential mode voltage gain from the prior analysis said that ADM was equal to minus GM times RD. So let's put these two together to find the common mode rejection ratio. Remember, the definition of the common mode rejection ratio is the differential mode voltage gain divided by the common mode voltage gain, or ADM divided by ACM. Let's substitute the values for ADM and ACM. Well, here we see that we can eliminate GM and GMRD, and our common mode rejection ratio is equal to 1 plus 2 GMRS. Now, we know that if RS is equal to infinity, in other words, the transistor is biased by an ideal current source, that the common mode rejection ratio would go to infinity. So we can say for an ideal differential amplifier, where it's biased with an ideal current source, and the circuit is perfectly symmetric, the common mode rejection ratio of the amplifier is infinite. Now this is perfect. This is what we desire. We want it only to amplify differential signals and to reject all common mode signals. And this is indeed what we have. So we're going to stop there for the day. In the next lecture, we're going to look at what happens when we start actively loading the circuit. So we're going to put current sources as the load, much like we did with our single-ended amplifiers. Talk to you next time.